All right, here's a video for the Unit 6 practice test. So starting with number 1, it says, for which of the following counts would a binomial probability be reasonable? The number of traffic tickets written on by each police officer in a large city during 1 month, the number of ones on a randomly selected set of 5 dice, the number of hearts in a hand of 5 cards dealt from a standard deck of 52 cards, the number of phone calls received in a 1-hour period, or all of the above. So in this case, the correct answer should be B. And the reason this is true is because the 4 conditions for binomial probability are met. Number 1, we can define a success and failure. So success would be getting a 1. Failure would be not a 1. Number 2, the condition that there is a fixed number of trials or observations. So in this case, a set of 5 dice, and it would equal 5. Or actually, sorry, that's the third condition. Doesn't really matter. So the actual second condition is that they're independent, and we know that rolling dice is independent. Okay, and then the fourth condition relates to the independence condition. The probability of success is the same. So the probability of rolling a 1 on a 6-sided 5 die, or on a 6-sided die, would be 1 out of 6 for every single roll. So since those 4 conditions are met, that would be the one where a binomial probability model would be reasonable. So number 2, this is basically a z-score problem. So it says X represents the profit made on a randomly selected day by a certain store. Assume that X is normal with mean of 360, standard deviation of 50. What's the probability that the store makes more than $420? So first thing we're going to do is we're going to figure out what is Z. So it's going to be 420 minus 360 divided by 50. So 420 minus 360 divided by 50 would give me a z-score of 1.2. And since we're trying to find more than 420, we're going to find the probability that z is greater than 1.2. So going to our z-score table, we're going to look up 1.2. And since we're looking for more than, we're going to do 1 minus this. So 1 minus 0.8849. So 1 minus 0.8849. So that probability is going to be 0.1151. So the probability that the store makes more than $420 is 0.1151. Then number 3 says, referring to the information number 2, what's the probability that approximately 70% on a randomly selected day the store will make less than how much? So in this case, we're working backwards. 70% is less than, so that's the area to the left. So we need to find the closest z to 0.70. So we're going to look here inside the table. We're going to find the closest thing to 0.70. So it looks like 0.6985. So the z-score for that probability is 0.52. So z is equal to 0.52. So now we're going to work backwards. 0.52 equals x minus 360 divided by 50. So to figure out x, we're going to multiply by 50. So 0.52 times 50, and then we're going to add 360. That's going to be 386. So the probability that approximately 70% make less than 386, or make the probability is 70% that on a randomly selected day the store will make less than $386. All right, number 4 says business evaluates proposed venture as follows. It stands to make a profit of $10,000 with profitability of $320. So this is an expected value problem. So I'm going to make a table. The first column is going to be outcome. So the first outcome is making a profit of $10K. Second outcome is making a profit of $5K. Third outcome is breaking even. So that's 0 profit. And fourth outcome is losing $5,000. And it gives us those probabilities. So profit of 10,000 is 3 out of 20. So this is probability. So 3 out of 20. Profit of 5K is 9 out of 20. Breaking even is 1/4. And losing 5,000 is 3 out of 20. So for the profit column, since this is just the profit, we're just going to put this here. So 10,000, 5,000, 0, and negative 5,000. So now to find the expected value, remember we multiply the profit times the probability and add those together. So I'm just going to do that in the calculator. So 10,000 times 3 out of 20 plus 5,000 times 9 out of 20 plus 0 times 1/4 plus negative 5,000 times 3 out of 20. So the expected value in this case is 3,000. All right, number 5 is another expected value problem since it's asking for our expected profit. So I'm going to make a table again. So we have our outcome, profit, and the probability. So in this particular case, let's see, we have the outcome of it being warm, an outcome of it being cool, and then outcome of being very cold. Okay. And then let's see. So it says if it's warm that day, she expects to make a $20,000 profit. So the profit in that case would just be $20,000. Cool, she expects to make a profit of $5,000. And very cold, she expects to suffer a $12,000 loss. So then it gives us the probabilities for each situation. So it says the probability of it's being warm is 0.60. The probability of it being cold is 0.25. So it doesn't give us this third probability, but remember that these probabilities should all add up to 1. So to figure out that last probability, we can just do 1 minus 0.6 minus 0.25. So that means the probability of it being very cold is 0.15. So now to calculate our expected value, we're going to multiply the profit times the probability and add them together. So when we put that in our calculator, we get an expected value of 11,450. All right, number 6, it says a basketball player makes 70% of her free throws. She takes 7 free throws in the game. If the shots are independent of each other, what is the probability she makes 5 out of the 7 shots? So this isn't asking about expected value, which tells me this is a binomial probability problem. So for this, we're trying to figure out the probability that she makes exactly 5 shots. So we have to figure out what n is. N is the total number of shots she's making, which is 7. And p represents the probability that she makes the shot, which is going to be 0.70. So now we're going to put this in our binomial calculator. So n is 7, p is 0.7, and we're trying to find the probability that she makes exactly 5. So that's going to be 0.3177. So rounded, that's going to be 0.318. That's going to be B. Okay, 7, same situation, but now we're saying what's the probability that she makes at most 1 shot. So in terms of x, that's going to be less than or equal to 1. So it's the same n, which is 7, the same p. So we're going to go back to our probability table. At most 1 is less than or equal to. So less than or equal to is this symbol, and it's at most 1, which means it's just going to be 0 and 1 added together. So those probabilities are going to be 0.0038. All right, the next problem is again a binomial probability problem because it doesn't say anything about expected value. So it says a triangle test taster presented 3 food samples, 2 of which are alike, and is asked to pick out the odd one by tasting. If the tester has no well-developed sense of taste and can pick an odd one out only by guessing, what's the probability that in 5 trials he will make 4 or more correct decisions? Okay, so we're trying to find the probability that he makes 4 or more correct decisions. So x is greater than or equal to 4. N in this case is going to be 5 because that's the number of trials. And P, this is a little bit tricky because it doesn't explicitly say, but it does say that he's just randomly guessing one out of the 3 different food samples. So that means the probability of guessing right would be 1/3. Okay. So N is 5. P is going to be 1/3. And then we want 4 more, so we need greater than. So that would be 4 and 5 added together. So that's going to be 0.0453. So 0.0453. So that's going to be A. All right, number 9, 17 people have been exposed to a particular disease. Each one independently has 40% chance of contracting the disease. Hospital has a capacity to handle 10 cases of the disease. What's the probability that the hospital's capacity will be exceeded? So again, this is a binomial probability problem. Doesn't say anything about expected value. So we're trying to find the probability that X is, so it says exceeded. And if they're able to handle 10 cases, that means X is greater than 10. But we know that with GeoGebra, we have to rewrite that as greater than or equal to. So greater than or equal to 11. In this case, N is the total number of people. And in the first line, it says 17 people have been exposed to the disease. And then the probability of contracting the disease is 40%. So that means P is equal to 0.40. So we have 17 people. Probability of contracting the disease is 0.4. And we want the probability that X is greater than or equal to 11. So exceeded would be more than 10. So that would be 11 and above. So it would be these probabilities added together. That's 0.0348. So that probability is rounded. It's going to be 0.035. All right, number 10, it's asking for expected value. So we're going to create a table here with outcome, profit, and probability. So let's write out the different outcomes. So it says 2 or 4 is the first outcome. And the probability of rolling a 2 or a 4 on a single dice is going to be 2 out of 6. And then odd is the next outcome. And there's 3 odds out of 6 total numbers. And then the last outcome is rolling a 6, and that probability is 1 out of 6. So in terms of the profit column, it doesn't say that you're paying to play this game. So rolling a 2 or 4, you win $1. Odd, you win $3. And then rolling a 6, you win nothing. So now to find the expected value, we're going to multiply the profit times the probability and add those together. So in our calculator, that's going to be 1.83. So the expected value is going to be $1.83 per game. So that means if we play this game many times, we would win $1.83 per game. So number 11 says, referring to the game in number 10, what's your expected winning for 5 plays? So to figure that out, we're going to take the expected winning for 1 play and multiply that by 5. So 183 times 5 gives me an expected winning of $9.15. Oops. Would be the expected winning for 5 plays. All right, the next problem says, our attitudes towards shopping changing? Blah, blah, blah. Ask a random sample of 2,500 adults if they agreed or disagreed that they like buying new clothes, but shopping is often frustrating and time-consuming. It says 60% of all U.S. residents agree. What's the probability that more than 1,520 of the sample agree? So we're looking for a probability that more than 1,520 agree. For GeoGebra, we're going to rewrite that as greater than or equal to 1,521. And in this problem is the random sample of 2,500 adults, where the probability is 60%. So we're going to put this in our calculator. So n in this case is 2,500. And then P is 0.6. And then we're looking for greater than or equal to 1,521. So this is the greater than or equal to 1,521. So this case, it's a little slow because there's thousands of results here, but this is the sum, so 0.2014. So the probability that more than 1,520 of the sample agree is 0.2014. So same poll from the previous one. Now we want to know probability that less than 1,500 agree. We're going to rewrite that as x is less than or equal to 1499. So now we're going to change this to less than, and it's going to be 1499. So that's going to be 0.4913. All right, now let's look at number 14. So 14, they give us a probability distribution, and they tell us to calculate the expected value. So in this case, to calculate the expected value, we just have to multiply x times the probability and add them all together. So when we put that in our calculator, we get an expected value of 1.6. So then it says, referring to the information above, if 3 tech support people are using telephones, what's the mean total? So we're just going to take the expected value and multiply that by 3, which is going to be 4.8. For 15, what are the 4 conditions required for a binomial setting? So instead of going through that and writing it down, I'm just going to say it verbally. So remember, the first condition is that you can define a success and a failure. The second condition is that the number of the observations and trials are independent. The third condition is that there's a fixed number of trials or observations. And then the fourth condition is that the probability of success is the same for every trial or observation. So that you can get directly from your notes. All right, and here's the last problem. So it says Billy is taking his midterm, which has 25 multiple choice questions. He's not feeling confident at all. Billy knows he can get 5 question rights, and he has to guess on the remaining questions. Each multiple choice question has 5 options. So if he needs to get 13 questions correct to pass his midterm, what's the probability that he passes his midterm? So we know that the probability, or that he needs to pass 13 questions, but he can pass greater than or equal to 13 questions to pass his midterm. Okay, but one thing we have to consider is that he's going to get 5 questions right. So really, he's only guessing on 8. Or really, he only has to get 8 more questions right. Okay, so the test has 25 multiple choice questions. So n is 25, but again, since he knows he's going to get 5 questions right, we're going to subtract that from the total, which means n is going to be 20 in this case. So now the probability, it says that it's multiple choice and has 5 options. So if he's completely guessing, that means he has a 1 in 5 shot of guessing correct. So now we're going to use this information to figure out the probability that he'll pass the midterm. So the total number of questions he's guessing on is 20. Probability of him guessing right is 1 over 5. And he needs to get 8 or more questions right. So greater than or equal to. So that's going to be 0.0321. So the probability that he passes his midterm, if he's guessing on the questions, would be 0.0321.